Okay, in this little lecture, we want to talk about the terminology and definitions that we need to be using when we talk about multiple reactions. Now, in the last class, I had alluded to the fact that it's very unlikely that 4 molecules of HCl are going to just exactly bump into one oxygen molecule, boom, all at exactly the same time so that they can make this magic reaction. What in reality is going to happen is a sequence of reactions. And so when you have multiple reactions, the terminology changes. Now sometimes that series of reactions that are happening are beneficial because it took all of those to create our product gas of chlorine. But other times, as the one on the screen that we have here, the extra reactions are destructive. They're undesirable. Okay, so in these cases, some of the language that we need to use, we frequently talk about a desired reaction, which is our target. It's the one that we are hoping to have happen that's creating our product. In this particular case, I've shown the reaction of ethane to produce ethylene and hydrogen. Okay? Now, here's the problem, is when ethylene is created, that's great, but sometimes ethylene and ethane react together to make propane and methane. Sometimes when that ethylene is created, it releases hydrogen. The hydrogen reacts with the ethane to make 2 molecules of methane. So what we want is to create a language where we can describe how much of the desired product am I making and also know how much of these other side reactions are occurring. So the 2 primary things that we need to add to our kind of treasure trove of vocabulary and definitions is yield and selectivity. So yield is going to be a number, it's going to always be between 0 and 1, and it tells us how much of the desired product is formed as compared to how much of the desired product could have been formed in the best case scenario. So that means how much of the desired product could you have made if there hadn't been any side reactions, if all of the limiting reactant were consumed. That's the amount that goes in the denominator. How much you really made in the numerator. So it's always going to be a little less than 1. Okay? Selectivity is going to tell us how much of our product that we wanted was made compared to how much of junk was made, the undesired products. So in this case, methane, propane, etc., or I guess propylene. So this could take on any value. When it's less than 1, it means that I'm making more undesired product than desired product. That's not really the case we want. Okay? We are creating more junk than we are valuable product. This value ideally would go up towards infinity. The larger it is, the more desired product I'm making, and I'm making none of the junk. So let's look at how we can extend our concept of extent of reaction to looking at these multiple reactions. Now we'll stay with the same reaction that we've got right now, the reaction set, but what I want to do is extend the concept of the definition of that mole balance. So the number of moles in, or the number of moles at the end of product I equals the number of moles at the beginning of product I, plus the stoichiometric coefficient times extent of reaction. But I have multiple reactions. So I'm going to have a term for each of the reactions possible. So in this case I have 3 reactions. I'm going to have a term related to extent of reaction for the first reaction, the second reaction, and the third reaction. So let's just practice that for a moment. So I've named this reaction reaction 1, so I'll use squiggle 1 to represent that extent of reaction. This one I've called reaction 2, this one reaction 3. So please pause the video here for a moment And you try writing down expressions for Ni in terms of the amount that was in there at the beginning and the extent of reaction with the appropriate coefficients. Do this first for the the ethane is the one I did first, C2H6. See if you can get that one done. And pause the video. We'll come back and look at the next one. Okay, so this was my solution to just doing it for the C2H6. So the amount that's in at the end is the amount that's in there at the beginning. I don't have flow rate, so I can't do any more than that. It is consumed in reaction 1, so I subtracted 1 times squiggle 1. It's consumed in actually each of these, each time with the coefficient of 1. So minus squiggle 2, minus squiggle 3. So this is being used in all three reactions. It's being consumed in all three, so it's subtracted in each case. Now go ahead and do this for all of the other chemicals in this. Again, pause the video, come back and see if your answers match mine. Okay, so we had our first one there. The C2H6, our ethane, is consumed in each reaction with a stoichiometric coefficient of 1. C2H4, the ethylene, is produced in reaction 1, so I've said plus squiggle 1. There is no ethylene in this one, but in this last one it is consumed. So I've subtracted the consumption from reaction 3, squiggle 3. Hydrogen is formed in reaction 1, and it is consumed in reaction 2. It doesn't participate in reaction 3. Methane is going to be formed in reaction 2 with a stoichiometric coefficient of 2, and more is formed in reaction 3. And then finally we have our propane, which is formed only in reaction 3 with a stoichiometric coefficient of 1. So hopefully you were able to succeed with that. I do want to make a couple of comments about extent of reaction. I haven't really discussed this, but the extent of reaction I said was the same for all of the components in the reaction. But the value is going to depend on the way you write the reaction. So if you write a reaction a certain way and calculate the extent of reaction, it will be the same for all other components. But then if you compare your work to someone else who wrote it in a different way, they may have some different answers. So let's just take a look at that. So I just looked at, 2 molecules of A making B to form 2 molecules of C. And let's just say that our feed contains 2 kilomoles of A per hour and 2 kilomoles of B per hour. So my limiting reactant is A, and I have some excess B. In the product, they measure and they find that there's 0.5 kilomoles per hour of A. So I can do an A balance and figure out what the extent of reaction is for this reaction. So at the end I have 0.5. At the beginning I had 2. The stoichiometric coefficient is 2. It's being consumed, so minus 2 times the extent of reaction. And if you solve this, I came up with squiggle is 0.75. Okay, no problem, but now then let's look at what's going to happen if I change the way I write the reaction. This is another very valid way of writing the reaction. Maybe I just really would rather have a 1 here and I don't mind having fractional coefficients. If I have done that, for the same feed, same product, my balance changes because the stoichiometric coefficient of A is now 1. So 0.5 equals 2 minus squiggle. So that's the only difference. And of course the answer is squiggle is 1.5. Now I can still use this with this form of reaction to find out how much B and how much C I have at the end. But if I'm using this form, I need to make sure that I am using the stoichiometric coefficients from that reaction. So this is one of the ways where you can be doing things exactly right, along with a friend, and you compare work and you find out that you have very different answers, and yet both of you are still correct. Now, what we're going to be doing in class on Monday is applying these principles to balances on reactive processes, so with multiple reactions. So what we're going to be doing is we're going to be looking at systems where I have reactions. They may be steady state, they may be batch. My balance is that input plus generation is output plus consumption. And if this is batch, my input is at time 0 and output is at the final time. And I can write all of that using this formal balance, or I can shortcut it and this creates that balance for me as a formula. I just simply need to remember that I have to add up for all of the reactions, the stoichiometric coefficients times the squiggle for each reaction. The other thing that's going to be really key is that I have to remember mass is conserved, but moles of molecules are not. This formula takes care of that, but I cannot just simply say that in equals out. I can, however, work with atoms. So atoms are conserved, and when I do an atom balance, I can, in fact, just simply say input equals output. So on Monday, we're going to be using this extensive reaction for multiple reactions, applying our definition of selectivity and yield, so that we can begin solving problems with multiple reactions, and then extending that concept so that we can solve a system where I have multiple units, multiple processes, I have reactions, maybe multiple reactions, and perhaps even recycle or bypass. So that will be what we'll be working on Monday.